what if I told you that one of the most famous theories in all of physics, special relativity, might have been built on a simple oversight? That a brilliant thought experiment might have forgotten the most important character of all, the person who's actually watching. All right, so here's our game plan. We're going to start by introducing this idea of a forgotten camera eye. Then, we'll jump back in time to a sort of crossroads in science. And finally, we're going to see how this one little change completely transforms a classic thought experiment into something, well, something you probably didn't see coming. So first up, Einstein's forgotten camera eye. What on earth is that? Well, the central claim we're digging into today is that Einstein's incredible thought experiments might have overlooked a crucial detail. Not just the idea of an observer, in theory, but their actual physical position in space and the precise moment they see something happen. I mean, think about it. When Einstein imagined that light clock on a moving train, he described the clock, the light, the train perfectly. But where was the person watching it all from? Were they at the front of the platform, the back? And more importantly, when did the light from that clock actually hit their eyeballs? The whole argument here is that this isn't some tiny detail. It might just change everything. Okay, so look at this. On the left, that's the standard diagram you see in pretty much any physics textbook. It's clean, it's abstract. But on the right, we're adding what this theory calls the camera eye, a specific observer at a specific point in space. The argument is that physics is great at describing the event itself, but it kind of forgets about the whole process of recording that event. It almost treats seeing like it's instantaneous, but we all know it's not. It takes time for light to get from A to B. So how did we even get here? How did this supposed oversight happen? Well, the source material calls it a historical buttoning error. Like when you button up a shirt wrong and the whole thing is just a little bit off. The idea is that physics hit a fork in the road and chose a path that might have overlooked another crucial piece of the puzzle.
And this timeline shows that exact fork in the road. Way back in 1729, an experiment called stellar aberration suggested that the Earth is moving through some kind of light field. But then, fast forward to 1887, the super famous Michelson-Morley experiment tried to find this ether wind and came up with nothing. That led to this revolutionary idea that the speed of light is the same for everybody, no matter how they're moving. And that, right there, became the cornerstone of relativity. In the process, the idea of some absolute background and the nitty-gritty mechanics of how we see things was mostly put on the shelf.
Which brings us to this new idea, reality's electromagnetic stage. If we go back to that fork in the road and reconsider that other path, what does reality start to look like? Well, according to this theory, it looks like a fixed, absolute stage for everything to happen on. And here is the absolute key difference. In this model, the speed of light, c, is still the cosmic speed limit, but it's constant relative to this electromagnetic field itself, not constant for every single person, no matter how they're moving. The best way to picture this is the world's space in a 3D program like Blender. It's the absolute, unmoving grid that everything else exists and moves inside of. All motion is measured against that fixed background. Okay, so if we run with this idea of an absolute stage, it has a really profound consequence for how we see the world. It basically means that what you're perceiving at any given moment isn't now. Not really. It's a reconstructed picture built from old light. There's this fantastic Japanese term for this, damashie. It means a deceptive picture, kind of like an optical illusion. The idea is that our perception of reality is a damashie, not because it's fake, but because it's assembled from bits of information, light rays, that all have their starting points at different times in the past. So let's just walk through how this works. Step 1. Light bounces off of everything you can see, but it all leaves at slightly different times. Step 2. All those light rays travel through this absolute electromagnetic field. Step 3. And here's the magic. They all arrive at your camera eye at the exact same instant. And finally, Step 4. Your brain takes this flood of delayed signals and masterfully reconstructs it into the single, coherent image you call now. The source uses this great analogy of dried seaweed. It's all flat and crinkled, but when you put it in water, it blossoms into its true 3D form. Our brain is kind of doing the same thing with light. And now we get to the real climax of this whole idea. We are going back to Einstein's light clock, but this time we're going to look at it through the lens of the camera eye, keeping in mind that there is always an information delay. On the left, you've got the light clock we all know and love. From the perspective of somebody on the train, light goes straight up, bounces, comes straight down. A perfect vertical line. Simple. But wait, if what we see is a reconstruction of old light, is that straight line what an observer on the platform actually perceives?
Or is it something else entirely?
So to visualize this, we need to use a pretty clever tool from math called complex space. Now don't worry, the name sounds way scarier than it is. Just imagine you're drawing a map. You have up, down, and left, right. Complex space just adds another direction, past, future. It lets us draw a picture that includes not just where something is, but when the light from that thing had to leave to get to our eyes. It's literally a map of the information delay.
And here is the big reveal. In order for an observer to see the entire path of that light beam all at once, the light from the points farther away had to have left earlier to arrive at the same time as the light from closer points, right? So when you plot that journey on our special map that includes time, the path is no longer a straight line. The information delay itself actually bends the perceived path into an arc.
Whoa, okay. That is a pretty radical way to rethink things. So let's just take a step back for a second and put these two models of reality right next to each other, just to make the difference crystal clear.
So let's break this down. On one side, you have mainstream physics. Here, space-time itself is flexible. It can bend and stretch. The one thing that's absolute is the speed of light, which is constant for every observer. Then on the other side, you have this camera eye view. Here, the electromagnetic field is the absolute, unmoving stage. The speed of light is constant, sure, but it's constant relative to that field. And the observer isn't just a point of view. They're an active participant, reconstructing an image of the past from all these delayed signals.
And that really just leaves us with one final massive question to chew on. Is reality the state of things as they actually exist out there? Or is what we call reality simply the story that light tells us when it finally reaches our eyes? A story that is always and inevitably a picture of the past.